Okay, now we get to apply synthetic division to evaluate a polynomial. This is really a pretty cool concept. So we're going to do an example just to show you how easy this is, first of all. So let's say determine f of 17 using synthetic division. If f of x, the function f of x, equals 4x to the 6th minus 71x to the 5th plus 51x to the 4th plus 2x to the 3rd minus 35x squared plus 20x plus 2. Okay? Now, I'm gonna say this up front. If you're told to use synthetic division, use synthetic division. But f of 17 just means plug 17 in for x, okay? Now, you can see that if you do that, you're going to have to raise 17 to lots of powers here. So trying to do that even by hand at all would be difficult. So sometimes synthetic division is easier, and you'll see that using synthetic division eliminates raising numbers to big powers. Okay, so I'm going to show you how to do this, and I'll explain why it works. So all you do is you take the function itself, you take that like it's a dividend in synthetic division. So we have 4x to the 6th, negative 71x to the 5th, positive 51x to the 4th, positive 2x cubed, negative 35x squared, positive 20x plus 2. No missing terms, no zero placeholders. And then the number, the input, is going to be what you put out here to represent your divisor. Okay? And what we're going to do is we're going to do the synthetic division. All right? And so to do the synthetic division, we drop our first coefficient to the bottom, and then we multiply and add until we're done with our last column. So 17 times 4 is 68. Negative 71 plus 68 is negative 3. 17 times negative 3 is negative 51. 51 plus negative 51 is 0. 17 times 0 is 0. 2 plus 0 is 2. 17 times 2 is 34. Negative 35 plus 34 is negative 1. 17 times negative 1 is negative 17. 20 plus negative 17 is positive 3. 17 times positive 3 is 51. And 2 plus 51 is 53. And that's our remainder. What we see is sometimes this is called the remainder theorem. Sometimes it's called the remainder theorem, depending on different textbooks. Well, f of 17 is just the remainder. That means if you go check this, if you plug 17 in for all of these x's and you raise it all the powers and you add and subtract, you're going to get 53. And you can see that in synthetic division we didn't have to raise any numbers to any powers. It was literally multiplying and adding, and that's it. So that's why sometimes synthetic division can be easier than direct substitution. Okay, now why does this work? Why does this work? So let's look at what this is telling us, what our synthetic division is telling us. So this is the why. Well, if we look at f of x, the original polynomial, f of x is the dividend, okay? We know the synthetic division tells us that, well, if I want to break that dividend down, I could take my divisor, which is x minus 17. Remember, this positive 17 represents x minus 17 times our quotient, which is right here, our quotient. And remember, we started with 4x to the 6th, so the first term here is x to the 5th. So our quotient is 4x to the 5th minus 3x to the 4th plus 0x cubed, so I'm not going to write that, plus 2x squared minus 1x plus 3. That's our quotient. So I multiply my divisor by my quotient, and then I add my remainder. Okay, so f of x can be written as this polynomial here, but that's also equal to this form here. They're the same exact thing. You could check it. You could simplify this bottom version and get the original. But look at this. If I want to know f of 17, right, that's what we're trying to figure out is f of 17, then I plug 17 in for x. So I get 17 minus 17 times. It doesn't matter what goes here. And then I've got my plus 53. The reason that it doesn't matter is because 17 minus 17 is 0. And 0 times whatever is here all vanishes to 0. So we get 0 plus 53, which is 53, and that's what we see up here. So when you do this process, evaluating a polynomial by synthetic division, the key is to remember that the input is what goes here as your divisor, and that the answer is simply your remainder, and that's why it's sometimes called the remainder theorem. Okay? Let's try one more. Let's determine f of 2 if f of x equals x cubed minus 8. And yes, this one's very easy to do by direct substitution. Okay, if you plug in 2 for x, you get 2 cubed, which is 8. 8 minus 8 is 0. But let's just run through the process with synthetic division. Again, I take my input and put it in the divisor position in my synthetic division, and then my dividend is 1x cubed plus 0x squared plus 0x minus 8. We've got some 0 placeholders there. We drop our 1, and then we multiply and add. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8. Negative 8 plus 8 is 0. And that is f of 2. So f of 2 equals 0. Okay, which we knew by direct substitution. So this one was easy to see both ways. But what I want to point out here is there's something special that happens when you get a remainder of 0. Okay, when the remainder is 0, the input is a 0. This is important because if you ever want to check to see if a number is a 0, you just check to see if the remainder is a 0. That's so important, I'm going to type it here. If we want to check whether a number is a 0, use synthetic division and look at the remainder. Okay, so two things in this video. We see how to evaluate a polynomial synthetic division. In other words, we know how to get the output of a function, a polynomial function, with synthetic division. Furthermore, if that remainder, that output is 0, then the original number is a 0. So in this case, we say that 2 is a 0 of x cubed minus 8. All right? So it's a handy way to check for zeros as well.